Welcome to this video on the topic of vectors in 3D space. In this video, we're going to have a look at how we can model a sphere using vectors. Now the way in which we're going to do this is we're going to look at two forms in which we model a sphere, that being a vector equation and then secondly being the Cartesian equation. After which we're going to look at three examples of how we can model spheres given different situations. During these examples, we'll employ our technology such as our calculators and the website GeoGebra 3D to assist us in the modeling process. Now starting off, spheres may be modeled using vectors. Now the first way in which we're going to look at how we can model a vector is using something called the vector equation or vector form. Now put bluntly, the vector form of a sphere can be written as the absolute value of an arbitrary point in space R subtracted by the center of the sphere C, which is equal to A, which is the radius of the sphere. Unpacking what this all means, let's draw ourselves a diagram. Let's say that we are interested at looking at an arbitrary point in space, which is from the origin O to point C. Point C representing the center of our sphere. Now the way in which we go from O to C, we're going to describe it using the position vector C or little c, like so. Now, adding on to this diagram, what we need to do is we need to put in a point P. And we'll just say this point P is an arbitrary point, let's say there, and it's going to be represented, say, here on the sphere. And to get from O to P, then what we're going to be doing is we're moving along the position vector R. And point P is located in space as X, Y, Z. It's just arbitrary. It's not particularly important where it is. All we know is that it lies somewhere on the surface of the sphere. Now moving from C to P, we have a vector that is something like this. We'll have to do. So to go from C to P. And the length of C to P is going to be A. So the length from C to P is simply A. So what we have over here is the diagram that describes the situation of the vector form shown up here. Now, what we're going to do is we're going to convert this vector form into the Cartesian form. To convert to Cartesian form, what we first do is we start off with our vector form shown over here. So, position R, take away position C, is equal to A. And I might just rotate this around the equal sign on the next one. What I'm now going to do is I'm going to convert these into their vectors over here. So O to C, O to P. So that's going to be shuffling it around. O to P, subtract O to C. Alright, now next step, we are going to employ one of the identities that we have, which is the square of the absolute value of a vector is the same as saying the dot product of the vector against itself. So let's say the absolute value of vector u squared is the same as vector u dot u. Doing this, what this will turn into is a squared as shown. Now if we calculate the dot product of CP dot CP, then what we get is, firstly, C is an arbitrary point. So let's just say that this is alpha, beta, gamma. So that's the positions. So this is going to become X, take alpha, Y, take beta, Z, take gamma, which in turn will become something that looks very similar to a locus in 2D space. So what we've got over here is our Cartesian form of an equation that describes a sphere. So this describes this situation up here, and this is equivalent to this. Alright, now that we've had a look at how we can get these two forms, let's look at the practical application of these. So let's look at an example. Example 1. Find the equation of a sphere with center at c -3 to -1 and radius of 5 units. To do this, we need to identify our center and we need to identify our radius. Using this, we'll first plug this into our Cartesian equation here, and then we'll model it using our vector form up here. Starting off, we're going to say that x minus alpha squared plus y minus beta squared plus z minus gamma squared, where alpha, beta, and gamma represent the points C over here. Subbing these values in, we're going to get A is equal to 5 because it's a radius of 5 squared, and then we're going to get x minus 3, which becomes a plus y minus 2 squared plus z minus 1, which becomes plus 1 all squared. And thus what we have over here is the equation that models the sphere that has a center of 3 or -3 to -1 and a radius of 5 units. So this is our Cartesian form. Converting this into vector form, we can draw it as a column vector, or we can write it as its component form. To do this, we simply go the absolute value of, and on the first one I'm going to write it in its column form, so it's going to be the arbitrary point r subtracted by our column vector 3 minus 2 1, and all of this is equal to 5. So this is our vector form. And the final way in which we can do this using our vector form is we can say the absolute value of arbitrary vector r, and then we're going to have in brackets 3i minus 2j plus k. So it's in its component form, and that's all equal to 5. So it's still vector form, however it's broken into its components. Nice and easy. So that's example 1, finding the equation of a sphere with a center of -3 to -1 and has a radius of 5 units. Alright, let's have a look at the next example. Example 2. Find the equation of the sphere with a radius or with a center of a -3, 5, 2 and touches point B 2, 1, 5. What we're looking at here is we are looking at the situation where we have an arbitrary point A and point B. And point A is going to serve as the center for this diagram here. So it's going to be point A, and it's going to have points -3, 5, and 2. And let's just assume point B is out here. It's neither drawn to scale nor accurate, but it's more of a representation of what we're trying to do here. So A to B, and what we're going to find is that we're going to touch something like that. Okay, now that we've drawn up the situation, what we need to do is we need to figure out the distance from A to B, which will reveal to us our radius. Because we already know our center, all we need is our radius to model this. So our radius is the distance from A to B. The way in which we can calculate this is we need to go A is equal to the absolute value of vector AB. Vector AB, of course, equaling first B, it's 215, subtract minus -3, take 5, and take 2. Simply putting this through our calculators. Say up we come, run matrix, we go to options, map vec, then across into norm, which will give us the absolute value of a vector. I go exit twice, math, map vec, and I'll go 3 by 1. So 2, 1, 5, subtract, and go -3, 5 and 2, done. And we get the answer 5√2, which is roughly 7.07, so that's alright. So we go 5√2. Remember, this is a distance with unspecified units, so we just call it units. Alright, now that we've got our center, which is at point A, and we know our radius, which is 5√2 units, we can simply plug this into the Cartesian form of the equation. So it's going to be 5√2, and all of that is squared, equals, and then we can go x, take, our point A is -3, so that becomes +3, plus y, take 5, all squared, plus z, take 2, all squared. So what we've done is we have discovered the Cartesian equation of the sphere that models the sphere that has a center of -3, 5, and 2, and touches point B 2, 1, 5 on its outer surface, which also happens to have a radius of 5√2 units. So that's example 2. Now, having a look at what this would look like on, say, GeoGebra, we say up we come, we type in our points, A equals -3, 5, 2, I believe it was, and then B, 2, 1, 5. The vector that we're interested in is from A to B, so we can say AB equals vector A to B. We want to know its length, we'll call it A equals length AB, which is 7.07 as we discovered before. And then because of that, we can simply type in the Cartesian equation. So A squared is equal to x minus 5 all squared, should be a +3, my bad, minus 5 all squared, plus z minus 2 all squared. And thus what you can see is we've modeled the sphere such that it has a center at A and it's got B on its outer surface. So this is the Cartesian form here. Alright, let's have a look at example 3, something slightly more tricky. In example 3, we want to find the points of intersection for a line described with the equation shown over here and the sphere described with the vector equation over here. What we're effectively looking at is we're going to have a sphere and we're going to have a line through space. It's going to look something like that, perhaps. And we are searching for the points of intersection. So intersection 1, we will call this point A, and intersection point 2, which we'll call B. So we're going to get 2 points of intersection, because if this line does hit the circle or hit the sphere, then it's got to go in and then it's got to come out. Now we are presented with equations that are in forms that aren't particularly useful at this point in time. So what we're going to do is we're going to solve this by first converting the line into its parametric equations. Then we will convert the sphere into its Cartesian form. We will then substitute the Cartesian equations for x, y, and z into the Cartesian equation of the sphere, and then we will solve for lambda. That will reveal to us the 2 values of lambda that reveal the positions of A and B. Alright, so starting off, firstly we need to convert the line into its parametric equations. Now looking at this, we're going to get, I might even just convert it into its vector equation first, because that's a little bit easier to see. So we're going to get x, y, z. The points that they cut through are defined as just the three standing ijk, so it's component forms. So it's -2, 3, and 2, plus lambda 5, 2, and -3. So this is our line over here. The line itself is defined in its parametric form as -2 plus 5 lambda, y equals 3 plus 2 lambda, and z is equal to 2 minus 3 lambda. I don't need to define lambda again because it's already defined there. Okay, so these are the parametric equations for the line. Next, we need to convert the sphere into its Cartesian form such that it's actually useful. Okay, so what we find is that this is the center of the sphere here, so 3i minus k. It's in its component form, so I'll convert it to a row vector, and this is the radius here. So the sphere is going to be defined as the square of 7, which is equal to 3i, which is the x component. So that will be x take 3 squared plus, there's no j component, so it's just y take 0. We'll leave that out, so it's just y squared, plus z component is plus 1 because it's minus in here. So that's our sphere. Now, sub the parametric equations into the sphere equation and then solve for lambda. This is going to look like 7 squared over here in brackets. And the last, we find that we have a giant mess on our hands. Now, if I were to try and solve this by hand, I might get it right, but knowing myself, I'd probably get it wrong because I'd make a mistake somewhere. So what I do at this stage is I say, up we come to my calculator, and I'm going to use the solve n feature in here. So I go exit to the top menu, option, calc, solve n. Then I'm just going to plug this equation in, and I'll get my calculator to solve for lambda. Place x in place of lambda. And then I tell it to solve for x. Does a little bit of thinking, gives me a warning that there's multiple solutions, and here are my solutions here. So negative 0.100, so that's going to be, that's the 3 dp, and we're going to get 1.574. Alright, it's not ideal that it's known its exact form, but it's just going to have to do for what we're working with here. So what we're going to find is one lambda is going to reveal this location, and the other one will reveal B over here. Now to solve for this, what we need to do is we need to sub these values back into the parametric equations. Now a simple way in which this can be done is we can simply store these values within the memory of our calculator. So I can say minus 0.100. I'll hit the store over here, and I'm going to put it in location A. Next, I'm going to type in the parametrics. So -2 plus 5a, 3 plus 2a, and then finally 2 minus 3a. And lo and behold, this reveals the location of the intercepts. So therefore point A, which is a point of intersection, is going to be minus 2.5, 2.8, and 2.3. And B is going to be, all I need to do is go up and change the value of A that I stored in my memory. So we said that was 1.574, thus revealing the values. Done. Now checking our calculations on GeoGebra, we simply say up we come. We can get rid of all of these. Alright, so the first point was, well, the first equation was minus 232 and 52 minus 3. So this is the line over here. Yeah, so that's our line. Next we need the sphere, which is minus 3, 0 plus 1. And what we're looking at are the points of intersection here and here. And what we found was the first one, for having to flick back, is going to be 5.87, 6.148, and then minus 2.722. And lo and behold, that's our first point of intersection there. It's not going to be exact, especially after I moved it. It's not going to be exact because this was an estimation here, or approximation, but it's going to be pretty close. Now the second one we said was negative 2.5, 2.8, and 2.3. And lo and behold, here we have A, also sitting on the surface of the sphere, thus demonstrating the method in which we calculate the points of intersection of a line and a sphere. That being, you simply arrange them, the line in parametric form, the sphere into Cartesian form, substitute the values or the parametrics of the line into the sphere, solve for the unknown, and then sub that back into the parametrics to find the exact points. So in summary, what we had a look at in this lesson was firstly the ways in which we can model a sphere, that being the vector form, and then secondly the Cartesian form, after which we had a look at a few examples of how we can model a sphere using the center and a radius, 2 points, and then the points of intersection.